Okay, so this is the moon part 2, and although you probably knew quite a lot of the material that I put in part 1, part 2 might have some surprises, so I hope there's some new things in here. We're actually going to look at the moon first of all by using some colour filters, and even with amateur equipment you can start to see some difference in the colour of different bits of the surface of the moon. This picture here has just got a hint of the fact that it's not entirely grey over the whole of the surface. You can see that some of the mare have a slightly blue tinge and others are more of a greeny grey in this particular photograph. Again here, the same region of the moon, we've got the Plato crater at the top left there, and the Alpine Valley, Mare Imbrium. The bottom left, we've got the big crater Copernicus, about 250 million years old, and typically everything's looking very grey. But if you really play with the filters and go to town on it, you can reveal what the eye cannot see, which is really quite dramatic amounts of colour. If you try hard to pull the colour out of the images, you start to see here that there really are differences between the different regions. So you can see the crater Copernicus there has brought up new material, and that's got a different hue to it. Some of the older regions have got a very brown colour, and others that much deeper blue. Now they tell me that this can be used to identify different minerals on the moon, and we'll talk about that in more detail as we go through. But I really just want you to enjoy some of the photographs and showing the moon in a different light, making it really rather more interesting than just a mass of grey craters. So here's the Mare Imbrium again, and we've really processed the colours quite neatly. You can see the Plato crater top centre there, flooded with the brown material. You can see the blue colours down there towards the wrinkle ridges, and yet the Bay of Rainbows on the mid left side of the screen there, again that same reddy brown colour. But if you look at the crater over there towards the right hand side of Mare Imbrium, you can see it's almost got a pale greeny colour, and we think that what's going on here is we're bringing up materials that may contain metals from deeper inside the moon, perhaps bringing some of those materials with the incoming space rock and changing the overall composition of the moon. So it's important to think some of these materials may have been from the ancient part of the moon, and others may have been delivered from space. And you can start to piece together some of the history of the moon using that. Here's one of the brightest areas on the moon. This is the Aristarchus region, named after the scientist that we were talking about in part 1 who worked out the distance to the moon. There's been some volcanic activity here, and also a relatively new, very bright looking crater. We can see some old collapsed lava tubes, rills, running through the brown region, and then that's completely surrounded by that bluer colour material going off in different directions. And so here it looks like the older material from the volcanic period is the brown substance, and we can actually identify that as feldspar, whereas the blue regions, those are titanium rich rock. Titanium's really quite a common element, but not the most common by any stretch of the imagination. And it's quite interesting to see just how much titanium there is in some regions of the moon there. And again, it looks like the impact crater has probably brought some other minerals either with it or up from underneath and given them some of the greener regions. Again, a complete mixed terrain here. We've got some very interesting yellow and red colours, as well as more of that blue titanium rich material. and down at the lower regions there, some of those endogenic craters and a big long rill running across the surface here, picked out nicely. There we can zoom in on it and you can see how the lava tube has collapsed, and a lot of little craters have punched holes right through the top of it there. Quite amazing. And we've got wrinkle ridges and all sorts of other features. But the colour really does help you see all of these different regions. Here's the full moon again, that same photograph. And just to show you, we can colorize the whole thing. And again, you can see some of the seas are blue, others are brown. We looked to start with at the two that were mostly brown, and that suggested that that's the feldspar material, whereas the titanium rich rocks seem to only be in all of the other mare. That's very interesting, isn't it? And then, of course, we got the very bright impact craters again with their rays showing fresh new material stretching out around the moon. Now, here's a picture. I think they've gone rather too far here, perhaps. This was NASA that produced this one. Using data from the Galileo spacecraft, they have not just gone for false colour, but complete psychedelia, really. And again, they're picking out and identifying the different regions. We got the titanium-rich blue, the feldspar, the recent impact ejecta, the basalt lava flows, and the more recent lava flows, all picked out in different colours here, using more or less the same colour scheme. They really haven't gone in and coloured it in. They've just enhanced what colour is naturally there to the absolute maximum here, I think. So if we look at what this is all telling us about the composition of the moon, we find that the lunar soil is 40-something% oxygen, 20-something% silicon. Well, that's fairly natural because silicon dioxide is sand, and many of the minerals are silicates, which is SiO3, silicon and 3 oxygens, combined with some metals. And then we've got iron as the most common metal to combine with the silicates, calcium, aluminium, magnesium, and then lumped together are all the rest of the elements under other there. And so you can see that that titanium doesn't actually turn out to even be one of the foremost common metals in the lunar soil. If we compare different regions of the moon, the lunar lowlands and the lunar highlands, with the Earth's crust, again, we can see that the shape here is more or less the same. We've got round about 45% oxygen from all three sources, roughly the same proportion of silicate, aluminium. Well, interestingly, the lunar highlands are containing more aluminium than either of the Earth or the lunar lowlands, whereas when you go to the lowlands, it's the when you go to iron, it is the lunar lowlands that stick out as being different, and the Earth matches the lunar highlands. So that's slightly curious. And then, well, calcium, they're all different. Sodium, the Earth's got a lot more sodium for some reason, and potassium, well, those two are very similar, so no surprise there. And magnesium, well, it's following along the trend in some ways, but not in others. And then massive spike for titanium there on the lunar lowland, whereas the Earth and the lunar highlands contain very little. So there's something been going on here that's quite interesting from the point of view of how this chemical composition must have got created. And that leads us on to the question of the origin of the moon. So there are various theories being put forward over time. One is that it formed along with the Earth, condensing together out of the same nebula. So inside the group of rotating gas and dust, the solar nebula, when the solar system formed. Perhaps the Earth condensed out of a particularly overdense region of it, and the moon condensed at the same time and just naturally formed hand in glove with the Earth. Another idea is that it was a wandering body that formed somewhere else and just came too close to the Earth and got captured into orbit by the Earth's gravity. Well, it's another possibility, I suppose. The third idea was that it was split away from the Earth, and even that splitting occurred because the Earth was spinning very fast, and the centrifugal force might have detached a lump of it that then flew up into orbit. And people have sometimes suggested that that might have come from the Pacific Ocean, because that looks like a big hole in the ground on the Earth. But we now know that's not right, and that the Pacific Ocean hasn't always been there because the continents move around. And anyway, the mathematics of the energy and the rotation speed of the Earth and so forth just don't really add up to it being able to throw a large object like the moon away from itself out into orbit like that. It just would not have the energy to do it. So I don't think this sort of idea here is really tenable at all. Well, the other way it could be split off from the Earth is by a collision, and this is probably the most popular explanation, that way back around about 4,000 million years ago, when the Earth was fairly young, a stray planetoid smashed into the Earth and blasted material off the surface, which then condensed into the moon. Well, as we've seen, we know the chemical composition of the moon, and we know it very well, not just from studying the light and the spectra and the colours of the moon, but we can also analyse the 300 and something kilograms of space rock that the various Apollo missions brought back with them, and determine the exact chemistry from the different samples back here in the lab. And when we do that, we find that things match between the Earth and the moon really quite nicely. If we look particularly at the different amounts of the different isotopes of different elements in the material, and this chart on the left is an oxygen isotope plot. So it's looking at how many of the oxygen atoms are carrying 2 extra neutrons along the horizontal axis, the oxygen 18, and how many are only carrying 1 extra neutron, the oxygen 17, up the vertical axis. And you can see the little red stars for the moon samples are all on a nice straight line, and that straight line matches the entire chemistry of the Earth incredibly well. Whereas various meteorites that we've collected that we know have come from Mars don't match. They're the little green diamonds, and they're above the line. And we even have samples of the asteroid Vesta, and those are clustered down as the blue squares, and they're below the line, so they don't match. So we're fairly confident that that signature of oxygen and of lots of other elements that have been analysed in the same way all points to the fact that the moon's surface and the Earth's surface are made largely of the same stuff. But right back at the beginning, we also realised that the moon didn't have the same density as the Earth. Back in part 1, we talked about the fact that the moon is a 64th of the volume of the Earth, but it's only 1/80th of the density. And that, we think, is because it only has a rather tiny iron core. It didn't really end up with a huge iron core in the same proportion to that the Earth has, even for its size. The answer, putting all of that together, is that it's not likely to be a captured asteroid because the chemistry doesn't match, particularly those oxygen isotopes. We don't think that they co-condensed together. Probably if they had, the proportion of iron in the core would be about the same, and the moon seems to have been shortchanged in terms of iron in its core. So the commonality between the Earth's crust and the outer layers of the moon in terms of isotopes suggests that it was split away from the Earth somehow, and we ruled out the spinning too fast idea. So it really leaves us with what we call the big splat, which is that the Earth formed about 4.5 billion years ago, and then about 4 billion years ago, the Earth was hit by another small planetoid, perhaps at a glancing angle, and blew a lot of the material out into orbit, and the two metal cores of the incoming planetoid and the proto-Earth probably merged together, giving Earth a very large iron core, but not much of the iron was blasted into orbit. And so when the moon formed out of the debris and the impact ripped away that was thrown around the Earth into the orbit around it, probably didn't have so much of a proportion of iron, and that explains why the moon is iron deficient in its core. So the Earth's iron core was left behind, and the moon from the orbiting debris didn't get much of it. Okay. So this is called the Theia hypothesis. Theia, they have chosen as the name for this theoretical planetoid that perhaps formed in the same orbit as the Earth. That's the same 93 million mile distance from the Sun, at one of the semi-stable Lagrange points, L4 and L5. These are shown in the first diagram at the top right. 60 degrees ahead and 60 degrees behind the Earth, there's a semi-stable point at which you can park an object, and the combined effect of the orbital motion and the Earth and Sun's gravity will keep it roughly in that position. But it's not entirely stable due to perturbations from the other planets of the solar system. And so it would tend to wander away and then back again, and further away and back again. And eventually, if it wanders too far, then it will come close to the Earth and collide with it. And of course, it would collide at a relatively modest speed, so not likely to completely destroy the Earth, but enough to blast a lot of the material up out into orbit to subsequently regather under gravity and coalesce to form the moon. So that's the idea of the Theia hypothesis of the moon's formation. And lots of people have done computer models of that. Now, from time to time, we hear stories about the Earth perhaps having more than one moon. And this has been a favourite sport of people for some time. 1846, Frederick Pettit of the Toulouse Observatory actually reported that he had seen a second moon of the Earth, and this became called Pettit's moon, and it's referred to in Jules Verne's book there, From the Earth to the Moon. They take off in their spacecraft fired from a giant cannon, and they pass by Pettit's moon on the way to the Earth's actual moon. So it had become accepted as a real thing for quite some time. Of course, it's not really there. So I'm not quite sure what it was that Frederick Pettit was observing. I mean, he had a thoroughly good professional observatory at his disposal, so I don't really know what he was looking at. But interestingly, if the Theia hypothesis is correct, then at one time on Earth, it would have perhaps had a selection of moonlets and indeed a set of rings. After Theia had impacted and blasted all of that material out into orbit around it, there wouldn't have been one large chunk to make one large moon. It would have probably resulted in the Earth having rings and dozens of small moonlets of varying sizes, all flying around, all on different chaotic orbits. But over time, they've all either hit the moon or hit the Earth. It's possible some of them might have been ejected from the system from random collisions between them, but nevertheless, probably most of them were collected up by the gravity of the Earth or the Moon in the process. Now, when we look at the Moon, and we have a look at the maria, the seas, not just with visible light, but with other methods. So we've got three images here: the visible image picture on the left that we're familiar with. We've got a radar height map where the orbiting satellite measured the height of the ground. Blue is low-lying, and followed by yellow, and then red for the highland regions. So you can see that, in fact, the maria are coloured in blue and are therefore holes in the ground, which is consistent with them being caused by impacts. But we can also look at the gravity of the Moon. They put a couple of space probes orbiting round the Moon and measured how their orbit changed due to gravity anomalies, which are over or under dense regions in the gravity of the Moon. And you can see that there are quite significant features for these gravity anomalies aligning with some of the larger mare, the deep blue coloured splodges on that right hand image. And also there's a big blue irregular rim running almost right round that face of the Moon, which we'll have a look at in a moment. So we know that these mare are all the results of giant asteroid impacts on the Moon. They crashed into it and made enormous craters a very long time ago, very ancient indeed. And it's possible that these are the scars of the Moon collecting up all of its smaller sister moons that were formed in that giant impact. If we look at the ocean of storms, the biggest of the seas on the Moon, over on the what we see as the left-hand side when we look at it in the sky, and we can put the gravity anomalies on there in blue for you, you can see that they ring right around the outside of the ocean of storms. And they were probably lava running in those cracks. And it suggests that there was a mega impact that perhaps nearly destroyed the Moon. So perhaps one of the Moon's larger sisters smashed into the ocean of storms there and created that enormous disturbance. And we still see the result of it today. And then, of course, smaller impacts have happened on top of it, which have confused the picture somewhat. But of course, until we had the space age, we couldn't see the far side of the Moon due to the Moon always keeping one face turned towards us. But now we have images from spacecraft that have gone round and brought these marvelous pictures back to us. And it looks very different. Yeah, I know it looks grey and it's covered in craters, but there are a couple of sort of weedy looking mare, but not the same sort of structure that we see on the near side. So the two halves really are rather different. When we look in the gravity anomalies again, we can see that the Moon has on the far side been peppered by a whole range of small craters and large craters and medium-sized ones in between. And we can do that same thing of looking to see how they overlap and stack. But we can also see down at the South Pole there the huge dent in the bottom of the Moon. That's called the South Aitken Basin. And all of this points to a structure of the Moon where the small core of the object was formed slightly nearer the near side of the Earth to the Earth than the far side, and the crust on the near side of the Moon is much thinner than the crust on the far side. And that's due to the distorting effects of the gravity of the Earth, which really confirms that the molten Moon cooled down and solidified in orbit around the Earth. So I think that's very, very good evidence, again, pointing towards the Theia hypothesis. Certainly points away from the idea that the Moon formed somewhere else and was subsequently captured, because if it had formed in isolation, it would have been symmetrical in all, because the gravity would have been equal in all directions, and it wouldn't have had a large distorting effect of a big neighbouring planet like the Earth to contend with. Now, of course, that thin crust on the near side explains the mare and why there are so many of them, and that's because most of them manage to puncture right through the thin crust, and then molten rock would flow up through the holes and flood them. Whereas with the crust being much thicker on the far side, even large impacts failed to penetrate through the solid layer down and release the molten rock out to do that flooding process. So it kind of all fits together. But if we look round at the South Pole, that's South Polar Aitken Basin that I measured, again using this colour-coded gravity, the blue being a very deep hole. Here we have a 6 kilometre deep depression in the undersurface, the south polar region of the moon. So this again looks like another impact of a fairly large object, possibly another one of these sister moons of the moon being absorbed as a slow speed impact. They would nudge into each other. If you had high speed impact of something of this sort of size, it might even destroy the moon. So the fact that it was a slow speed impact points towards the fact that it could have been co-orbiting round the Earth at the same time, and that would result in a much lower relative velocity, so a much more gentle impact. But we do have other objects that are playing this same game of following the Earth around in its orbit. Got a little animation going on here of an asteroid called Cruithne that perhaps isn't really a moon of the Earth, but is nevertheless a companion in space, because Cruithne takes exactly 1 year to complete its red orbit, as we do on the blue orbit there for the Earth. And so we keep meeting up. At this point, we're coming close together. We don't quite intersect, and we move further apart again. But if you look at the left-hand diagram, where instead of allowing the Copernican view of the sun being stationary in the middle, we make the Earth appear stationary, you can see how Cruithne creates one of these kidney-shaped yellow traces of an orbit. So it comes close to the Earth and then wanders away again. So from our point of view, it's definitely almost captured by the Earth's gravity and then escapes again. So not really a second moon that's survived this long anyway. But there is an object that has been in orbit around the moon, around the Earth for some time, and that is asteroid 2016 HO3. It's discovered back in that year, and this animation shows the path of HO13 around the Earth and around the Sun. So you could argue that it's orbiting the Sun, and the red line is the orbit, but it really looks pretty much from the yellow trace relative to the Earth that it's in fact orbiting round the Earth. Now the distance is really quite a lot further away from the Earth than our regular moon is, and it's not necessarily a permanent attachment, because the perturbations of the gravity of other planets may well throw HO13 back out to going back into a proper solar orbit and tear it away from the Earth. But we think that it's going to follow us around at least for a few hundred years. So you can see there it says it's 9 million miles away from the Earth. So that's 36 times further away than our moon is. Right, so this brings us to the end of the discussion of the moon. That's all I could think of to say about it, but I hope you've enjoyed it. It certainly, with those colour photographs, shows it literally in a new light, and adds an extra dimension of interest to observing the moon and imagining that some of those regions that are titanium rich may well have come from the impact of asteroids from another part of the solar system with different chemistry. Other parts of the moon's surface may have come from the sister moons from the Theia impact being captured and forming back together to the one moon that we have today, which may explain why we have those differences in the chemistry of the different regions of the outer surface of the moon. So I'll bring that to an end there. I hope you enjoyed that. And